Hey physics friends, let's talk about flowing fluids. So we've already talked about stationary fluids, aka static fluids. One of our fundamental things that we consider when a fluid is flowing is that what goes into a pipe has to come out of a pipe. It's effectively conservation of mass. So the number of gallons going in, you will have the same number of gallons going out. You will also have the same flow rate, which is represented by the letter Q. If we imagine just like a cylindrical pipe, the volume of that pipe is going to be the cross-sectional area A. Generally, it's going to be like a circle, right? So like pi r squared, multiplied by the length, delta x. So volume is going to be area times just this generic length. When we consider this as like a flow rate, so like with respect to time, there is a cute little simplification that we can do, right? Where you see that, delta x over delta t, right? That is velocity. And so that is the continuity equation right there. Wow, I think I did it in about like 20 seconds. Amazing. So area 1 times the velocity in that spot is going to be equal to area 2 times the velocity in that spot, right? So if we have a pipe that changes diameter, right, the bigger area is going to have a slower velocity than the smaller area, right? Because we have to push the same amount of fluid through both sections of the pipe. And this is a little weird because, like, as the pipe narrows, that means the fluid must accelerate. Well, where there's acceleration, there must be a net force. Well, what could the net force possibly be from? Well, it's got to be from, like, other parts of the fluid itself. So as your water molecules go through, like, this region here in the middle, right, where the diameter of the pipe is decreasing, that force is primarily from the fluid that is behind it pushing it forward, which means that it's kind of counterintuitive, but where the diameter is big and the velocity is slow, that's actually a higher pressure region than the narrow part, right, that has the fast velocity. And this is probably the most counterintuitive thing about flowing fluids, is that a fast velocity means low pressure, not high pressure, right? Because you think, if something's moving fast, it's gonna like come out with like a lot of pressure. That's actually like your brain is like misinterpreting it, but that's not what that means. A high velocity is very effective when it comes to like pressure washing. Not really. You have a high pressure inside the pressure washer so that the velocity comes out like really fast, right? Which is what is effective in like cleaning like dirt off your sidewalk or the side of your house. So it's kind of like a misnomer, right? Your pressure washer really should be called a velocity washer because it's the high speed water that's getting all of the grime off of whatever you're trying to clean. So if you're okay with that idea, let's keep going. And in fact, even if you're not okay with that idea, I hope that in this next derivation, I'm able to prove it. So here we have a pipe, right? I hope that you at least buy that, where you have a big diameter, the fluid is slow, and where you have a narrow diameter, the fluid is fast. So consider this little section of pipe, right? This fluid is flowing from left to right. If we were to consider an energy bar chart, right, for the fluid earth system, because I have to put the earth in the system if I want to consider gravitational potential energy, right? The left side of this pipe, it's got low speed, so it's got a little bit of kinetic energy. It's at the lowest point, right, in this little scenario, so we can say that our gravitational potential energy is effectively 0, right? So we have a little bit of total energy right here on the left, and then by some strange magic of physics, we seem to have increased our energy at the end because we know that when the pipe diameter narrows, it's got to go faster because we got to push the same amount of fluid through right? Both pipes, like the fluid's not going to accumulate anywhere, right? So our kinetic energy's got to go up, and our pipes, it got higher, right? So our gravitational potential energy is going to go up as well, which means our total mechanical energy has increased. Oh my goodness. So if our total energy changes, that means there has to be work done by something, right? It should be positive work overall because the total energy of our system increased. So, if you trust me, right, if we can assume that it's high pressure on the left-hand side, right, where the velocity is slow, and low pressure on the right-hand side where the velocity is fast, right, check it out, right? We would have positive work being done, right, from the fluid that's on the left, and some negative work, just a little bit, of negative work that's being done by the fluid that's on the right, essentially resisting, right, the flow of the fluid. It's like pushing back against it. But that rightward push, like from behind, is bigger, and overall, more positive work is done, right, by the high pressure side than the low pressure side. Let's do the work energy theorem, right? We can't really do conservation of energy here because we obviously, right, have a change in total energy as this fluid moves through this rising, narrowing section. I'm going to keep this super generic. I know we said, we've got a little bit of kinetic energy and no gravitational potential energy, but since we're deriving, I'm going to go ahead and leave all of the terms, right, in our equation. So initial kinetic, initial grav, right, plus the work that is done by this pressure difference is equal to my final kinetic plus my final gravitational potential, okay? The work that is done by the pressure difference, you're going to have to dig back, right? Think about static fluids, right, and how to get force from a pressure difference, right? If work is equal to force times distance, right, pressure is equal to force divided by area. So force is equal to pressure times area, or specifically if we're looking at like the net force, right, it'll be the change in pressure multiplied by the area, right, and multiplied by the distance. Okay. We also know, if you recall from continuity equation just a moment ago, area, that's like cross-sectional area. Or actually, I should rephrase. In this case, don't worry about it so much. It's technically the area of like a water droplet that's getting affected, right? That's getting accelerated through this narrowing section. It's volume though, right? Area times distance is volume. So do a little bit of cute algebra there. And then we can divide everything by volume. And this is the equation that is on your equation sheet. This is Bernoulli's equation, but it's just a little bit of algebraic manipulation from the work energy equation, right? Effectively, you have like your pressure difference that's doing work, right? And then you have not like your full kinetic energy, but like your kinetic energy divided by volume, right? And then your gravitational potential energy, except it's like divided by volume. So it's in terms of density, right? Instead of just plain mass. So that is hopefully familiar to you, right? We've just kind of like put a little costume on it by dividing by volume. So let's get to some sample problems. And I guess some of y'all are going to go on and like become like doctors. So I guess we should talk a little bit about biology. It's not my favorite subject. So let's talk about arteries, right? I mean, this is the primary fluid flow, right, in the human body is blood, right, moving through your arteries, moving through your veins. And we are mostly focused on arteries. If you have high cholesterol, right, that cholesterol tends to get stuck to like your artery walls. And it creates an artificially narrow, there is a narrow region in your artery, right? And that's bad, right? Because you've got all this gunk in there. It's getting clogged, right? But in terms of like Bernoulli's equation and like pressure and flowing fluids, this is like exceptionally bad because you have that narrow region and you're going to have a high velocity there. And where you have a high velocity, you're going to have a low pressure. So your arteries, like the walls themselves, the forces on the artery walls should be balanced, right? You don't want to collapse your blood vessel. You don't want to burst your blood vessel. We'll talk about that in just a moment. So if you look over there on the right, you've got like your normally flowing blood, right? And you've got like the tissues that are surrounding your arteries. And if you consider like the total force on your artery wall, like it should be balanced, okay? In the region though, where we have low pressure, right, then the force that the flowing blood can exert, through the cholesterol and onto the artery wall, it's going to be smaller, which is bad, right? So now you have like an unbalanced force on this artery wall, and so your artery is going to like crush more, which is going to then constrict your passage some more, which is going to increase the velocity, which is going to decrease the pressure, and which is going to constrict it more and more and more until your artery becomes fully closed. Like, it's not 100% full of cholesterol. I mean, that definitely would be very bad for your health, right? But even like a partial blockage can end up like totally clamping your artery shut, right? Due to like this property of flowing fluids that's represented, all right, in Bernoulli's equation. So that's bad, right? Here's another terrible example. Terrible as in very bad for your health, not like terrible as in, well, the physics is kind of cool. And, hopefully we can use physics to kind of like fix both of these problems, right? We would like our artery walls to be nice, smooth, happy physics world, same size pipes, right, all the way, because it's easy to keep it in equilibrium if everything is like the same, right? So if you have an aneurysm or the beginnings of an aneurysm, right, your artery wall is a little weak, and so it has a tendency to bulge, right? And so with that increased area, right, okay, well then the velocity of your blood is going to be slower in that region because of the continuity equation. And then because of Bernoulli's equation, or you can think of it from like a forces perspective, right, where you have a slow velocity, you must have a higher pressure in that region. And so then with that higher pressure, then that means that the force exerted like on the inside of your artery by your blood on the artery wall, well, that force is going to be bigger than the force that like your tissues would just like apply, right? Holding your artery at supposed to be the same diameter. So you're going to get like a bigger bulge. And with the bigger bulge, you're going to get a slower velocity. With a slower velocity, you're going to get a higher pressure. With the higher pressure, you're going to get more bulging until you have this aneurysm burst, which is really, really bad. It's like very scary. I don't want to think about it. It's just, biology, not for me. Don't want to think about it. Let's throw some numbers on here, right? Let's actually do a mathematical example. Let me show you how to use Bernoulli's equation to calculate what that pressure difference is between like a normal part of the artery and this bulging almost aneurysm, right? We don't have to worry about like the gravitational potential energy part of Bernoulli because I've drawn both of my arteries as just like flat, right? So we only have to worry about pressure and kinetic energy divided by volume. So if the bulging area is 1.7 times as big, okay, we can use that to determine the velocity at that point, right? We would expect the velocity in this region to be slower, right? And we would apply the continuity equation to determine what the velocity is as it moves through that aneurysm. So, or bulge, about to be aneurysm. So if the normal blood velocity is 0.4, right, we almost double our area. We almost have our velocity. So the velocity as it moves through the bulge is going to be 0.24. Once I have this velocity, then I can plug that in, right, to my Bernoulli's equation. I am looking for delta P. I know that P2 is bigger than P1, so I'm going to do P2 minus P1, not the other way around. I had to look up the density of blood. I think it's 1,060 kilograms per meter cubed. Crunch those numbers, we get a pressure difference of 55 pascals, which I don't think that's a lot, but I don't know. I mean, I Googled a little bit. I'm not really a biology person. As the biggest thing that it told me was, as you get older, your arteries become less elastic, and so they can't handle like these changes in pressure as well as like when you are young. So just something to keep an eye on. I don't know, like, I don't even know how you like look for like bulges in your arteries. You have a lot. Oh, I don't want to think about it. Let's go back to physics. You have perhaps done a lab that looks like this, perhaps involving a 2-liter bottle and a push pin. Let's establish Torricelli's equation. It's a special case of Bernoulli's equation. We're going to imagine a water tower. And so the water tower actually has to be a little bit open to atmosphere, right? Otherwise, it's not going to drain properly. When you do the lab, you can't have the cap on your 2-liter bottle. Otherwise, it's going to mess things up, right? Because we want the surface of the water up top there at location B, right, to be at atmospheric pressure, right? Because it's in contact with air, you can always say, okay, it's just atmospheric pressure, 1 times 10 to the 5th pascals, right? With the valve closed, right, you think back a little bit, oh yes, static fluids, sure, right? The pressure at the valve, right, is going to be equal to your atmospheric pressure plus rho g times the depth, right, that is at location A, right? Or in this case, you could say, well, it's going to be the height of the water column. Okay. When you open the valve, you can't use the static fluid formula anymore, right? You have to use Bernoulli's equation. And the cool thing is when the valve is opened, that water becomes in contact with the air, and the pressure at that point is going to be atmospheric pressure. Okay. Writing the full form of Bernoulli's equation, because we have pressures, we have changes in height, we have velocity, right? So let's do all 6 terms of that and then kind of simplify from here. At position A, this is like the lowest point in my problem because I made it that way. So I'm able to cancel out that gravitational potential energy term, right, at location A. If height is 0, then we don't have to worry about that. We said, right, that the valve up top is open, right? So that point B is atmospheric pressure. And when the valve is open, point A is also atmospheric pressure. And so we're able to cancel out both like pressure and pressure B. It's on both sides and they are the same, right? You subtract them, it turns into a 0. Okay. Now, here's the big assumption for Torricelli's equation. This is the answer to one of your lab questions. You can use Torricelli's equation when the velocity of the height of the water column, if that changes very slowly, right? Because like the volume is really big. Like if I open this valve at A, it's going to take forever, right, for the whole water tower to drain. If you think about the height of the water column, it's going to decrease very, 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 very slowly. And that's what we're considering the velocity of B to be, right? So let that be 0. And then we simplify. We get 1/2 density times the velocity at A, so it's the velocity at the nozzle, squared, is equal to rho GH. I assume that it is water all the way through, right? And so if that's the case, you can cancel out your densities, you solve for velocity, and you get something that's hopefully extremely familiar, right? That the velocity is equal to the square root of 2g times the height of the water. This looks just like conservation of energy, right? If you drop a tennis ball, right? The velocity at which it impacts is going to be equal to the square root of 2g times the height from which you dropped it. Makes a lot of sense, right? When you consider that Bernoulli's equation is just the work energy theorem equation, except, well, there's no pressure difference, so there's no work done by the pressure difference. So if there's no external forces, then it becomes conservation of energy, which is nice, right? This is the second way of determining the velocity at A. Like if you don't want to do projectile motion, right, you can use Torricelli's equation in a situation like this. Whew. That is all I have to say for now. Yeah, thanks for listening to me today.